So, welcome to this new module, that is module number 5, and in this module I will discuss about the various component design. In the components I am not going to discuss about the converter design, because already we have seen complete converter analysis, required features, then we saw the various output voltages, etc., mall operation of converter, etc., that is done. Now, in the component design I will discuss mainly the filter part, the filter design, DC line design, and also I will not discuss about the transformer design, because the transformer is more or less similar to the AC, is just a conventional transformer, especially some special features already I have discussed in the previous lectures. So, this module is mainly dedicated to this your filter design as well as the DC line design. To design the filter, we must know what are the various type of harmonics in the system, because the purpose of the filter is to filter out the harmonic components, means other than fundamental components. To know this, we have to go for the harmonic analysis, and what are the various elements those are generating harmonics in HVDC system are three major components. First one is no doubt is the converter, which is the huge source of harmonics generation. Another is your transformers, and those are this OLTC transformers, that is called the converter transformers. And third is your AC system itself. Normally it is believed the harmonics generated by AC system or generators are very less, but it is also generating some sort of harmonics. It is very higher order due to this non-uniform of the flux in this, or you can say non-uniformity of the field winding in the stator. So, it generates some of the harmonics, but it is very low order and very low magnitude. That is why we assume our supply system is balanced and it is free from harmonics. Second one is your transformer. The transformer here is the special transformer, where we have to go for the more flux density. Normally it is designed to give more leakage reactance, so that it is can protect your the fault, it can limit your fault current as well. So, you know, this transformers, once it is saturated, because all the transformers normally they are operating at the knee point. So, if the flux density is uniformly here, your flux, if it is your flux, I can say phi, it is perfect sinusoidal. So, your excitation current will be here, will be like this. And you know, this is not a, this is a current, that is excitation current. Here it is not a sinusoidal, and thereby itself this will generate some harmonics. So, this is also a source of harmonics. But again, if you will see the component here, some of the components here are the magnitudes are very less, but some of the components like the second and your even the third order is a quite bit here in this harmonics component. So, these are there, but again the magnitudes are very less, so we can just not discuss here. My concern here, that harmonics generated by your converter circuit, because these transformers are also in your complete AC system, but only the problem here, this harmonics generated by the normal conventional transformer is less compared to the converter transformer, because this converter transformer works for a high flux density. So, more flux, more distortion, more harmonics. So, to analyze the converter circuit which is generating harmonics, here there is two types of harmonics are there. One is called the characteristic harmonics, the components of harmonics means other than fundamental, and another is called your non-characteristic harmonics, that is other than this. So, your characteristic harmonics, here you can see the DC side we are having the harmonics component n into p, where n is any integer and p is your pulse number. And this harmonics is not a current harmonics, it is your voltage harmonics, means there is a distortion in the voltage. We require the DC, smooth DC voltage, but it is not there. It is as you know, here the voltage whatever it is appearing here, it is just like here in, if it is 6 pulse, so in one cycle there is a pulses, so it is a voltage magnitude. Because we have assumed our current here is smooth, this is your ID, here it is your VD. So, in the DC side we are having the voltage harmonics, and we are assuming the current is ripple free because we are using the smoothing reactor, and that is why there is no harmonics. In AC side here we are assuming that we are giving the balanced supply, means your AC voltage, here is your balance, this is your VA, here it is your VB, here it is your VC, this is the balance, and you know the qualification of the balance already I have discussed in when I was describing the converter circuit analysis. Here it should be the magnitude of each phases should be equal, and it is displaced by 120 degree, and it will be the phase sequence here the positive, it will be in your clockwise. So, the positive sequence voltage is given, and here there is no harmonics. This is a balanced sinusoidal. But due to this we are having the current here, we are having some sort of pulses. If you have see here again the different type of configuration of your transformers, here it is basically the 2 pi by 3, here is your pi by 3, here it is your again 2 pi by 3. This is basically any phase current, I can say A. So, it is having now current harmonics. So, this here that is why I have written this is AC side, and AC side we are having the current harmonics, DC side we are having the voltage harmonics, and they are categorized by this, especially if you are assuming there is no overlap. If the instantaneous here is there, so we can analyze and we can see we are getting the harmonics here. This is your NP, that is your H component, means for H1, H2 we can keep on going, and here we are getting NP plus minus 1, the H component here we are going, we will just see it and we are going to get it. Now, to analyze this we have to make certain assumptions, and those assumptions are here as already I stated that AC supply is 3-phase balanced, means again the EA, EBC here we are giving the balanced supply, already I defined the definition of this, and the DC current is a constant, that is a ripple free, we have assumed this, and also it is assumed that all the valves are igniting at the equal intervals at 1/6 of your per cycle. Here we are going to analyze for 6 pulse converter right now, and if we are having the 2 6 pulse converter connected by star star and star delta transformers, 2 bridges are there in series, then we can have the 12 pulse, we will see. The commutation inductances are equal in all 3 phases. Here we want to say that this is your the EA, this inductance here LA, it is equal to your this inductance here LB, and so on. So, it is your LC. So, these are equal in the magnitude. So, from these 2 assumptions we can say our AC voltage and the DC current has no harmonics, and some other observation we can make from these assumptions as well as the converter topology. The first 2 already we saw that here there is no harmonics here. Here it is also assumed that overlap angle is same for everyone, because here these values are same and the DC current is constant. In the beginning we will take there is no overlap, and then we will analyze the harmonics component for the current, and then we will see it. The ripple in the DC voltage has a period of here of again 1/6. Hence, the harmonics of direct current are order of 6 and its multiple. So, here the 6 pulses, so it is here we are going to get the 6, 12, 18, etc. AC current of 3 phases have the same wave shape, but the displaced by 120 degree, because A is this one. So, we are getting the same wave shape, but your IB here, this IA current, here it will be displaced by 120 degree. We also find from this wave shape that it follows that this is your theta, that is omega t. Here we will find that the f theta plus 180 degree is equal to minus of ft. You can take at any point, you will find, let us see here, if it is 0, you add 180 degree and you will find the magnitude will be the negative of this one. So, this is the property here whatever we are getting, although this wave shape is for your star star configuration. If you are saying for your star delta, no doubt here shape is changed, but still that value holds. And this shows that if this property is there, so with the Fourier analysis we can say there will be no third harmonics component at all. We will also see in analysis, but even though you find this property holds, means you do not have the triple N harmonics third components. No, this shows that there is no even harmonics in the AC current, means there will be no even harmonics, means you do not have the 2, 4, 6 etc. harmonics, you are having 1. But the triple N harmonics will be also absent. We will see based on this property we can say the triple N harmonics will be also absent, and we will prove also for the various cases. Now, here it is written the phase difference of any hth harmonics is s times for that of the fundamental component. What does it mean? If your phase difference means there is a phase here is shifting by your 120 degree, so it is multiplied by that component. So, your components, it suppose if I am going to write IA here, it is means there will be some component here, that is by 2, plus here we are going to get this sine and cosine components, and that here will get here cos s theta, here your h is equal to 1 to your infinite. Similarly, we are here component we are also getting ah, and we are going to get here bh sine s theta. So, basically this you can see s time it is going to multiplied. So, whatever the phase shift is there, it is a fundamental component, it is s times of that one. We will also see the various components here that is arising, means you can say the triple N harmonics are 0 sequence, always it called the triple N harmonics here. So, the sequence component here it is starting 0, since it is a 3 phase. So, we will have the 3 components 0, positive and negative. So, you can see here this is 0 component, so there is no DC at all here because upper and lower is same. So, average is 0. So, there is no DC current at all. So, 0 is this, then we are having the positive sequence, the 1 is the fundamental component and 2 is your negative sequence component. Is a general definition. No doubt with this wave shape we will having some component 0, like we will not have the second harmonics because there is no even harmonics because it is following that property. But we can analyze here this 0, 1, 2 this negative, then again third is a triple N harmonics, then your 4, 5, here 6, 7, 8 and so on and so forth. So, what will happen, your positive sequence component that is going to be added the positive here 3n plus 1, triple N harmonics will be 3 and your 3n minus 1 will be your here it will be your negative components. So, this is your I can say it is a negative sequence here is negative sequence component. Now, from this figure here it is a simple phase voltages, and now here you can see this is at this point your valve 5 and 6 were conducting, because you can see the current 6 here, the lower one is 6 and here is now at this point alpha can be fired because this is the commutation voltage of valve 1, that is your EAC, because the 5 is conducting, so C is coming. Just you can imagine here this is your 6. This is your 1, 3, 5, 4, 6, 2, A, B and C. So, 5 and 6 are conducting, then it is coming here C. So, EAC is the commutation voltage of valve 1, and at this point it can be fired, but we are delaying, let us suppose your alpha degree, and this alpha, that is why it is measured from here. Once it is taking, then current, if it is there is no overlap angle is 0, then instantaneously it will take the current I1 and it will reach here, and then it will go up to 120 degree and then it will be off when your 3 will be fired. So, at this point your 3 is coming into the picture. But due to the overlap, what will happen, this current will, there will be some commutation process between 5 and 1. So, the dotted line basically shows the due to the overlap period. And this current again when 3 is going to be fired, then this current is going to decrease and 3 is going to pick up. So, to analyze first, do not consider the dotted line, we are just whatever here I showed, you can see here we are getting this 120 degree here the positive pulse, and then here the 60 degree 0 current, and then negative here 120 degree. This is the case when we are having star star connection of the transformer. If you are having star delta, then the line current here that side we are going to have this much. Already the site already we have drawn also on this completely wave shape, and we are going to get in this fashion. Now, from here we can just analyze the harmonics component, and we can use, let us suppose this is your phase A current. Similarly, we can have the phase B current here because 6 is in the B, and then we can have the phase C currents here. And you can see it is only nothing but it is just shifted by 120 degree here. This is 60, this is 60. You can see from here it is shifted here the 240 degree. So, it is, as said, it is shifted only 120 degree here. So, let us take the ideal condition for this and analyze the Fourier and the components, that is here this Fourier series, and you can say the general Fourier series can be given by this equation. Now, this series is having a DC component, that is A naught. We are having a cosine component here, that is a magnitude here is AH. H is number of harmonics 1, 2, 3, 1 is the fundamental, and other than 1 is the harmonic component, and then we are having a cosine component as well with the coefficient BH. And these coefficients are defined as this formula, is the Fourier series analysis. Now, here with that diagram we have to determine the A naught, AH and BH components, but this AH and A0 can be easily understood by looking at the figure, because this average you are adding for into one cycle, it is 0. So, whatever this upper part, the lower part is same area, so add it, so average is 0. So, for this case here it is 0. Now, we have to go for AH and BH. Now, the AH and BH basically depends upon where you are choosing your axis. There is a possibility that if you are choosing your axis here, for example, you can see here, if you are choosing axis here, your component will be like this. The fundamental component will be like this. Or if you are choosing your axis here, this is just like a sine component. So, you can say a cosine and sine component depends upon where you are choosing your axis. If your axis you are choosing in the between of this, then there will be no sine components, it will be only the cosine component. If you are choosing here, you are having the sine component, there is no cosine component. Means there are the two properties, and the property number 1, it says that if you are having here f theta plus, here if I can write this property here, f theta, if it is equal to your minus f theta, good, then there will be only the cosine component, sine component, yeah, and yeah, it is only sine here, and cosine will be absent.
Minus of f of minus theta.
Yeah, minus here, yeah, that's correct, minus of this. And if you are having f theta is equal to your f minus theta, then you are having only cosine component. So, again it depends, if you are choosing here axis at this point, then you are having the cosine. You can see this follows here, because this side theta here, this is same magnitude is equal, and you can just move it. So, here if you are taking at this, so your sine component has gone, vanishes, and if you are taking this, means you are having here, you can say it is positive, it is negative, here is a positive, here negative. So, we are having that component, this is this component is present, here the cosine is present. And if you are taking any arbitrary here in between, then you are having both sine and cosine components. So, let us take, for analysis purpose, we can just consider our this axis here. I can take axis here as this point, the mid of this. So, from here we can, as per this analysis, we have to now find the AH value, and your AH, it is your 1 over pi integration 0 to 2 pi, here your f theta into your cos s theta d theta. Means this component here we can get from this axis here. We are taking axis here as a 0, and then we are analyzing, and here is a 2 pi or pi. It will be 2 pi because we are talking the whole cycle. Now, from this we can analyze. Now, it is 1 over pi. The integrate we can say from 0 to here we are starting 0. So, this value is pi by 3 because this pi by 3, this pi by 3. So, it is pi by 3. So, I can say ID into your cos s theta. Mind it, this h is not hyperbolic, is a number. Yeah. So, that is why I am separating here from here, there is a gap. Then we can, here it is 0, this value is 0. So, we can write 0 here. So, it is 0 plus, and this is your pi by 3 to 2 pi by 3, here 2 pi by 3 to 4 pi by 3 minus ID cos s theta d theta, because this is a negative current, this magnitude is ID. So, we are just doing this, then plus so here we are just coming, this is a pi by 3, pi by 3, pi by 3, here this, and then it is a positive. So, one is 0 here, that is your 4 pi by 3 to 5 by 3, plus here 5 pi by 3 to 6 pi by 3, that is your 2 pi, and here it is your ID cos s theta into this. Now, with this, no doubt B component, just we are assuming we are taking axis in such a way that we are having this BH is 0 and A naught was already 0. So, I want to write a general expression in terms of H, so that for putting the value of H, means we can get, solving this, I want to get what will be the value of A1, A2 to all, you can say AH value we can determine it. So, one is your fundamental component. This component, as I said, it will vanish, it will be 0, but we can also see from the analysis because it satisfied the Fourier analysis property. So, even will be 0. So, your A3 it will be also 0, A4 it will be also even, it will be 0, your A5 it will have some component, let us see, and your A6 will be also 0, and so on and so forth. So, here we have to determine these two components. We can also show what will be the value here. Now, yeah, A7 will come, of course, A7 will come, and we will see those values. Now, from here ID is common, so I can say AH, your ID by pi, this here, everywhere there is H. So, it will be, if you are integrating, it will become down here. So, it will be, I can write this H. Now, here it will be sine H, cosine will be sine. So, this will be sine 0 0. So, this will be your pi by 3 for this integration. This is 0, and for here I want to write here sine. Now, this value here is a minus. So, I can write here it is a minus your 4 pi h by 3 plus your sine 2 pi h upon 3. because this is 2 pi by 3 here, and this is going with, so it will be positive. Now here it will be plus sine 5 pi by 3 h, and now 2 pi sine 2 pi is 0 every time. What will be h value? So it will be 0, and we are going to get these 4 components. Yeah,
This one minus and minus.
it was minus here.
Yes, sir.
Oh, right, right. Because it is, this is a lower one, so it is minus, because this minus this. Yeah. Now, let us see for the simplicity, this is your A1. So I can say it is your ID upon pi, h is 1 here. Here we are going to have pi by 3, and pi by 3 means under root 3 by 2. Now this value sine 4 pi upon 3, what will be this value? This will be plus under root 3 by 2. This will be also under root 3 by 2. This will be also under 3 by 2. So we are going to get 2 under root 3 ID by pi. Means, and this component is the peak value, mind it, because whatever the component which is coming to your the Fourier series analysis, the value is the peak value. So here it is nothing but it is your I1 m, I can say. The peak value, it is not RMS value. To get RMS value I1, here it will be your under root 6 ID by pi. To see it here, I want to show that A2 will be 0, as even the property also shows it will be 0. Just put the value of 2 here, your ID divided by the twice pi. Here your sine 2 pi by 3 means it is your under root 3 by 2. Here 2, it is 8 pi by 3. How much this value? Plus or minus? 3 by 2. Here it is 4. It will be minus 3 by 2. Here it will be plus under root 3 by 2. And finally it is 0. Yeah, it is correct. We can see also A3 will be 0, A4 will be 0, A5 will be not 0. And once you are going for the A5, here I can say it is your A5. This is your 5 pi by 3. This value will be your minus 3 by 2. This value here, the 5 is 20 pi by 3. It will be your minus here. This value here you are putting 10 pi by 3. It is also minus. And this will be also minus. So we are getting this 5, and finally I can say it is by 5. So your fifth harmonics you can see it is your under here, this value we are getting. It can be also seen the fifth component which is appearing, it is nothing but it is your negative sequence component, and that is why it is negative term is coming. Seventh was in a positive. If remember here I wrote here 0, 1, 2, 3, 4, 5, 6, 7, your 8. Here this fifth was your negative component, and the magnitude here is coming negative. Here the seventh is the positive, and the value will come in the positive. So you can also verify and put the value A5, you will be getting the same value. So I can say your IA, the current will be your, this is your fundamental component that is copied outside, and we are giving the various, the fifth harmonics, we are giving seventh harmonics, but here the fifth component is negative, here it is, you can say is a positive, here again negative and positive, and so on. So, we can see the major observation here, that the component which are of higher order is divided by that harder component. So, this magnitude is keep on dividing and it is going to be reducing. So, the magnitude significant for our consideration is 5th, 7th, 11th and 13th. After that we are going to get what? It is your 17th and 19th harmonics will come, and then we are going to a 23 and 25th and so on and so forth. So, those are very small magnitude, and that for that we never design the filters. But for these 4 components we have to design the filters, and because they are the significant, even though 1 upon 13 means 10% is this, here it is 8%, here it is almost 15% or so, approximately 15, here it is approximately 20% of the fundamental components are there. So, this is the case when we have our star-star connection, and we are talking, mind it, if your transformer is there here, so we are talking at this primary side of the transformer. No doubt in this star-star connection, this side is the same than this side, because the same unity ratio, if you are assuming a unity ratio, whatever is here that will be coming here. But if you are going for your star delta here, so we are going to go for the phase current here, and that phase current is coming to line current here, because this phase will be this phase, this will be your this whatever the phase. So, here this component is different, the similar to here whatever we are getting, but inside the phases is a different, because it is this minus this current is this one line current, and that just I showed you here in this figure. Here you can see this is your, now I can say it is your IA current. This is the case when we are having your star delta configuration, and in this case you can see if you are taking your axis here, then your this is your cosine component, here it will be your cosine component will be coming. If you are taking your axis here, then it is your sine component will be coming. So, the analysis, similar analysis can be done, and you will find here the current here IA, now I can write here I capital because it is a star delta, and the component here is just changed with a different one because there is a shift of 30 degree. So, here this component now becomes positive, this component become negative, this was the as negative here, which was the negative here, and this becomes positive. So, you can see the components are same, average value is same, everything is there, only here the components which was the earlier the positive, it is going to be negative, here it was a positive negative, but this is the same. And now you can see, to minimize the harmonics, if you add these two together, then these components will be cancelled, only we are going to get this one. And this is the main feature of the 12 pulse converter, that you can use this star star and star delta transformer, these components will be get cancelled, and we are having only means pulse number now it is 12, and thereby we are getting again our formula valid, that is your NP plus minus 1, and it is we are going to have 11 and 13, and then we are going to have 23 and 25. So, 23 and 25 are gone because we never designed the filter for that, because the component is very less. So, but we design 11th and 13th. If you are operating your 6 pulse converter, then you have to go for at least the 4th, and even though required, then you can go for the 17th and 19th as well. So, in the 12 pulse here, you can see this is your, this is the condition for your star star, here is your star delta, and if you are adding, you can get here the 12 pulses, and you are just getting this component here. So, your IA is here. Now, the question, if you are adding these two currents, the value should be the double of this. For example, this one, sorry, if you are adding this current and this current, now for the fundamental what is happening here is a 2 cos theta. This is cancelled, here again the twice of this, here the twice of this. So, we are getting the twice of this, but this twice of this is not, we are trying to equalize that the per unit power given by 6 pulse is equal to if 12 pulse, then the magnitude here can be written in this form again, the fundamental component. So, the current is halved here, means whatever the power it is coming out is the same for power. So, current should be reduced here, half of this, and here that is why it is half. So, this value is there. But if it is not so, then you can add together the 2 here, the 2 will be there multiplied by this. So, this is your component, and you can see 11th, 13th and 15th are appearing. So, we analyze this current harmonics here in the AC circuit, and with this assumption that there is no overlap angle. Now, what will be the impact? In actual case, this overlap angle will be there. Maybe the value is very small, but it cannot be 0, because we are having a lot of inductances in the circuit. There is a commutation inductances. So, what will be having the effect of overlap? Basically, that decreases the harmonics, but it introduces some uncharacteristic harmonics. And uncharacteristic harmonics, those are other than characteristic harmonics, which we analyze. We analyze whatever here the components, those were the characteristic harmonics, that is NP plus minus 1. Other than that, it will be arise due to the overlap, and also the magnitude of the harmonics will be reduced. So, what is the this uncharacteristic harmonic? Basically, here it is stated that converter produces harmonic of all orders. It is not the 1, 5th, 7th, etc. It is all the orders, and some DC component also arises here on the valve winding of the transformer. Why it is? You can see this the DC component. This may not be equal. You can see this is here. You can see this area may not be equal to this area, and sub component may be arised. There will be some DC component, but very small this area, because this is here decreasing, this is increasing. There may be possibility that you cannot have the complete, and some small amount of the DC component will be there. And also here this will decrease your, it will decrease your the values as it is said, and there may be some DC component as well. But the uncharacteristic harmonics components are very less, low magnitude, but sometimes these harmonics also create some problem into your system. But it is very difficult to know what will be the magnitude of these uncharacteristic harmonics. All these varies depending upon your U angle, depending on your alpha angle, depending upon your beta angle, and otherwise your inverter angles. So, all the DC angles, if it is changing, these components are changing. In the previous case, we analyzed for any value of alpha, there is no overlap angle, it was the, we are getting same 5th, 7th and 11th, 13th harmonics. But if your U value is changing, the uncharacteristic component will arise, and you have to, magnitude will be changed accordingly. So, people have analyzed for the different value of U, and they have plotted the shape, etc., and they found that these components are very, very small, but still sometimes they are significant. But they say it is a low magnitude. So, we never design the filters for this uncharacteristic harmonics. Sometimes they provide some filters, band pass filters, that is if it is a higher order, it may be passed out. But the tune filters we provide for the significant amount of the components like 5th, 7th, 11th and 13th, etc. So, what will be the causes of uncharacteristic harmonics? It is normally the valves are not fired at the equal intervals due to the unbalance of three-phase supply system. If your supply system is unbalanced, then the firing, because the zero crossing, if it is unbalanced, the zero will not fall up 120 degree displace of all the three phases. So, what will happen, because we are having the current controller, it is sensing the zero crossing, and based on it is giving the firing pulse. Thereby, if it is not equally spaced, means it is not 60 degree, then again you are having the different components as well. So, one is your overlap, another is your this unequal firing of the gate pulses. So, this will also introduce some uncharacteristic harmonic. Even though balanced circuit is there, you are using the electronic circuit to control it, to measure it, and due to this electronic circuit the zero crossing may be shifting here and there, and that may also introduce the uncharacteristic harmonics. Balance is very clear, because zero crossing is shifted, it is not 120 degree displaced. So, it may create problem, but even though it is balanced supply, you are using the power electronic device which is measuring, there is some signal processing and other things are doing, it may be 1 or 2 degree there is a displacement. and that displacement may again introduce some uncharacteristic harmonics. Here the control actions, I discussed about the HVDC controllers. The controllers basically see the current magnitude shifting here and there, then the firing angle of the coming valve, it is changed, so angle here is changed, and due to this change again we are introducing the harmonics. Especially the CEA control is very much prominent, because we are calculating this your angle well in advance, the beta, and we are maintaining the gamma, and if there is some problem, because the AC inverter side is a very weak system and it creates a lot of problem. So the CEA control introduce more harmonics due to the control action rather than CC, but both introduces uncharacteristic harmonic. The current controller, that is the rectifier side, CEA control used in the inverter side, but this is more prominent because more fluctuality is changing. Another here, the cause of this is the interaction of the characteristic harmonics. Already we are getting the characteristic harmonics, your 7th, 5th, 7th, 11th and 13th. If that is interacting with your fundamental component and there is some nonlinear elements, we are having the nonlinear elements in the power system, that is the nonlinear elements or inductors are still nonlinear, because they are coming here, then what happens, they are going to interact and that is creating problem. We are using so many other power electronics devices, like even though the filters are maybe having some power electronics devices, means if you are having any nonlinear element in the system, then interaction of these may also introduce some uncharacteristic harmonic. Another already I discussed, that is the saturation of the transformer. This we are having huge current which is flowing in the primary side, it is sudden jumps and sometimes sudden current is increasing, and there is a saturation of the transformer, and due to this saturation what happens, we are injecting harmonics into the system, and that it is not of this 5th, 7th, it is uncharacteristic harmonics. So the harmonics generated by transformer is not a characteristic harmonics. Now the effect of harmonic in general, it is not uncharacteristic or characteristic. Whenever harmonics are there in the system, means you are just your operation of your converter circuit is in trouble, because we require the smooth sinusoidal wave, because we are measuring the zero crossing, we are measuring so many other things based on our whole control circuitry design. So this is a operation may be disturbed, and sometimes the accuracy of CC control is also not guaranteed, and maybe it sometimes is unstable, because your controller is hitting here and there due to the change in this harmonic component. Shift of zero crossing, because your controller CEA and CC control is measuring zero crossing, this may be shifted and that may cause another problem. So it is a, you can say, cumulative process. Even though your zero crossing is shifted, your firing is different, again you are introducing more and more harmonics. So this is another one. Here interference with the harmonics telephone system, because if you are having higher order components, that may interfere your communication system, and that is another issue. Here if you are having more losses, then your elements like machines in terms of it is not only rotating, maybe static machine, your transformer will cause more loss. So the losses will be more. If there are some machines nearby, so there will be more heating in the system as well. The over voltage due to some resonance, because some of the components, because we are having complete RLC circuit in even the inverter side, this is your AC side I can say, and both converter and inverter side, and if that component is entering in that system, then there is a RC resonance, RL resonance, and that resonance may sometimes the huge voltage across either capacitor or across the inductor, and that may damage your elements. So the over voltage may cause, and that may create problem to your system. Another is your interference with the ripple control systems. Ripple control system, I mean to say that sometimes some utilities provide the power to the consumers at the off-peak hours. I mean to say that there is a possibility that we can use the same communication or wire business, that is a power line, for using the communication. Because if you are a user and power is to be given to you at the off time, so sitting in the substation, a person can switch it and the signal can go to your contractor and it may be on and off depending upon that. So if this component, because that harmonics component may be 1 kilohertz, it starts from 260 hertz to 1 kilohertz, and you can see your frequency component are falling in that one. If it is going there unnecessarily, then your conductor may be open or closed, and that may create problem to that one. So here the ripple control system, basically I want to say that sometimes consumers are being operated at the different time intervals, and that signal is generated from substation, and same wire, that the power line, is used for the communication giving signal of higher harmonics, and that harmonics may interfere with this, and you can get unnecessary opening or closing of the conductors, and thereby it will be operation. Now, how to judge that whether your system is perfect or not, because we are having so many components. Some components may be higher order magnitude, some are less. So there are some performance indices, or you can say the definition of the wave shape distortion or ripple are defined, and basic primary is your RMS harmonics. How much harmonics you are having in the system, it is defined. If you are talking about the AC current side, AC current here, it is your harmonics component, means all this RMS currents added, square of the RMS current, except your 1. Here is starting with the 2, added with all infinity, all the components, they are square of this added. Then if you are taking under root divided by the fundamental component. So this is the H1 index, is basically your alternating current. This can be also defined, this total I, that is effective value here, I is the effective RMS current, minus your fundamental component is square, and you are taking under root divided by this, you can get this H1 component. So this is one indicator how much H1 component you are having in per unit, because current divided by current, it is in per unit. Similarly, the DC side, here we are talking about the current. Similarly, we can talk about the voltage. What will be the, here now we are the VH, here the V1. So it is for the current, it is same. So we can just replace with the voltage also. In the DC side, it is your, here we want the DC value, even we don't want the fundamental component. So it is all the components of the current in the DC side, if it is there, then it is H1 to infinite. Here it's only the difference, here it is S2, here is H1, and it is divided by the average current, that is the DC current. We don't want the, because we want the DC current in the DC, we don't want even the fundamental component. So that is also treated as a harmonics with respect to the zero frequency here. And that is here again we can say total effective, the RMS current minus the average current is square under root divided by this. So this is your the total harmonics, RMS harmonics component.
DC side current is constant.
It's the average here. Now normally we want the DC is ripple free, but it is not so. So there will be some changes in the current, no doubt, but again the how much here this value S2 is there, it is a deciding factor. For the analysis we said that it is the DC is constant. If DC is here, this fixed value is ripple free, this value will be 0. Means if your S2 is 0, means we analyze here the component with the assumption that S2 is 0, because this value is not there. We assume this is ripple free, but it is not ripple free, it will be having some component, and based on that then we can analyze and we can find what is the value of H2. Another indice, that is indices are used, that is the deviation from the sine wave. Here this is a very easy, that is your instantaneous current I, that's total I, minus your fundamental component, instantaneous value you are just subtracting, and then you are taking the peak value of that, because your value is there some distorted wave shape, that is I instantaneous value, minus your perfect sinusoidal component, the fundamental component. Here we are talking the instantaneous value. And then we are taking where the difference, the maximum difference, because where is the happening maximum difference, then divided by your the peak value of that one, because here we are talking the peak value, and this your S3 component is defined. This is another criteria to see whether your system is well or not. Similarly, in the DC, if your current here is not perfect DC, it is having some instantaneous value, some current which is changing with the time, then divided by your subtracted by your average current, and then we are going to take the absolute where the maximum is appearing, because it will be changing, maybe somewhere it is 0 also, maybe negative. So we are talking here the maximum difference divided by your average value, for this is a direct run. Another criteria is to define it is to the peak to peak, and the peak to peak is very clear here. We are talking here this ripple, this I max minus I mean divided by this average value, and this is basically we are talking from the DC side, because this average here we are talking here. So, the difference where is the peak, and that is negative, and that is also it is called peak to peak value of the ripple. Another component normally it is defined, that is called maximum theoretical deviation from the sine wave. Here why we are going for this value, you can see here it is not a square, it is just similar to your previous case. The first case here you can see this, instead of squaring and adding here and squaring and then adding and then under root, taking under root here we are taking simply the RMS value of all the fundamental component other than fundamental divided by the fundamental value. This basically what happens, sometimes it is very difficult to get the phase angle of the components, because all square you are using. So, you know the phase angles of those components. Here some uncharacteristic harmonics are there, so it is very difficult to know. So, it is better to divide by this instead of squaring and adding. Here simply you added these components and then divide by this, you are getting S6 index. This is a similar if you are taking RMS value to RMS value, or you are taking here crest value to crest value. Crest means peak value. So, you are taking peak value of harmonics component added together, then fundamental peak, or you are taking this one. Here it is taken as a RMS value, but same index is some people take for the crest value and then they define in this way. So, this is basically the analysis part of harmonics. Now, the concern arises that how to minimize the harmonics, how to eliminate, how to mitigate this issue. One is to minimize the harmonics, we have to go for large number of pulses. Already we saw if you are using 12 pulse, you are just minimizing 5th and 7th harmonics. If you are going for 24, then again the harmonics your 13th and 11th are also gone, your 23 and 25th will be only there. So, we can go for the large number of pulses to minimize it, but again if you are going for large number of pulses, the complexity and the cost will increase, because you are adding the converters in such a way or you are designing such a way. So, the complexity is increasing, and therefore, always we go for the 12 pulse operation, where we are having your 11th and 13th harmonics, then we are having 23 and 25th harmonics, and we can design the filter for 11 and 13. Another is if you cannot minimize, you can fix number of pulse operation, then you have to use the filters. Now, again we will see the various type of filters are there. It is either tuned filters or it is a band pass filters, whether it is a series filter, whether it is a shunt filter. Again the various type of filters, it may be double frequency filters or single frequency filters. All these filters are basically now used to remove the harmonics that should not enter to your power system. If it is entering into the power system, already we saw the various problems that it may introduce losses, more losses, it will introduce interference, it is also maybe the resonance over voltage may arise, and other activities will happen. So, in this next lecture, we will discuss about the filter design, and we will see the various type of filters, and then we will see some problems as well on this issue. So, thank you.